Hi, my name is Sarai Guerrero, and I will present my poster at the G4 Symposium, Advanced Structural Materials, Synthesis, Properties, and Applications. Title, Real-Time Temperature Monitoring in the Concrete Hydration Process using a FABRY-PEROT interferometer. We propose a FABRY-PEROT interferometer, FFPI, point on the tip of a single-mode FCPC connector by attaching a polydimethylhexaxylone PDMS layer cavity of 78.85 micrometers as a temperature sensor. By leveraging the thermoelastic properties of PDMS, the optical path length (OPL) of the FFPI cavity changes with temperature variations. By analyzing the amplitude of the reflected signal of the FFPI in the Fourier domain, it was possible to establish a sensitivity of 2.4 10 times to -7 AU for degrees Celsius. The FABRY-PEROT interferometer-based temperature sensor was embedded in concrete prepared in a mold and interrogated in real time from the mixing stage to the setting stage. During this period, the results indicate temperature increments in the range of 5 to 35 degrees Celsius. Failures in concrete structure due to inadequate thermal control during the curing process result in costly repairs and safety risks. Temperature is a key factor in the setting process of concrete, influencing its specific weight, mechanical strength, wrinkle, and cracking behavior. Despite this, temperature monitoring in construction is often limited to manual measurements using traditional devices such as bimetallic thermometers, digital thermometers, and tape cake thermocouples, methods that lack continuity and are prone to errors. The construction industry demands new methods that enable reliable, continuous, and cost-effective in situ temperature monitoring during the concrete setting phase. Fiber optic sensors have emerged as a promising solution due to their immunity to electromagnetic interference, resistance to harsh environments, and ability to be immersed in water-containing mixtures such as concrete. Additionally, due to their small size, optical fibers can remain embedded in the concrete structure without causing structural damage in the medium or long term. This work explored the potential of using fiber optic technology, particularly FABRY-PEROT interferometer, to monitor temperature during concrete setting. To create a FABRY-PEROT cavity, an FCPC single-mode connector was used. The clean and polished surface of the connector was brought into contact with PDMS to form a hemisphere layer on the tip. As we can see in figure 1, there is a representative image of the sensor. In letter A, there is the connector with the PDMS hemisphere with a length of 78.85 micrometers. And in the letter B, we can see that this cavity was protected with a metallic cylinder. The device was embedded in a concrete dosage of 1:2 pure into a 7-piece mold with dimension of 200 millimeters in length and 100 millimeters in width. In figure 2, we can see that first we put a layer of concrete. Over that, we put the connector, and in layer B, we can see that the connector is covered with concrete. Real-time interrogation was conducted from the mixing stage to the setting stage, acquiring its interferometric response to temperature variations. In Figure 3, we can see the representative image of the experimental setup. Data acquisition was performed using the Hyperion SA255 by Micron Optics. Although the FABRY was able to detect changes in the interferometric pattern during the characterization, when the temperature increased by 5 degrees Celsius from 20 to 60 degrees Celsius, the resulting shifts in the pattern were complicated to follow up, as we can see in Figure 4. However, the variations in the amplitude and period of the reflected spectra were sufficient to produce variation in the Fourier peak magnitude. As we can see in Figure 5, there is the Fourier spectrum peak behavior of the FABRY with a 70.85 micrometers long polymer cavity under temperature increased in the left side and decreased on the right side. In Figure 6, we can see the characterization curve of the Fourier transform maxima for the FABRY, and increase in black dots and decrease in red dots are observed. Temperature variation were monitored by setting the connector in the Fourier domain at the time of concrete mixing, and in Figure 7 there is the representation of the Fourier transform peak maxima obtained from the mixing and pouring into the mold process. This is in the whole process. To determine temperature changes, an analysis was performed for each hour of the process. For this purpose, the equation from the increase curve in the characterization, Figure 6, was used like this. The difference in the magnitude delta y was calculated for each hour, as we can see, and since slope is represented in terms of delta y and delta x as p, by isolating delta x, the temperature variation per hour was obtained. In Figure 8, we can see a representation of the temperature variation per hour during the test, and there we have a change indicator. The sensor is capable of accurately measuring the temperature changes caused by the exothermic process in an environment where the optical fiber is prone to breaking. So the device demonstrates a sensitivity of 2.45 10 times 2 minus 7 AU 4 degrees Celsius. These results highlight the sensor's potential for reliable temperature monitoring in challenging conditions. All the authors are grateful to Secretaría de Ciencia, Humanidades, Tecnología e Innovación, CITI, and with the Centro de Investigaciones en Óptica. I will be presenting my poster on Tuesday at 18:30, so thank you.